What we're going to do now is a bit of a change of pace. This is an application to graph theory. So what's a graph? A graph is a bunch of nodes and edges which are connected. The edges connect the nodes like this. And associated to a graph is an important matrix called an incidence matrix. So you label the nodes 1 through 5, and you label the edges, and you make a matrix which has the number of columns is the number of nodes, and it has one row for each edge, and in the given edge you label the two corresponding nodes. So each row has two ones in it, telling you which of those two nodes form the ends of that edge. So the first edge goes from node 1 to node 5. So in this case you get this particular 7 by 5 matrix. Now a directed graph is the same thing, except that you put an arrow on each edge. So here's an example of a directed graph. And you label the nodes as before, and the incidence matrix for a directed graph is similar, except that in each row you put a 1 and a -1 to indicate that the edge is going from node with the 1 to the node labeled -1. So that's the incidence matrix for a directed graph, or sometimes called a digraph. So let's look a little bit more at these incidence matrices. Let's start with an example. Let's take a very simple loop. 3 nodes and 3 edges. The incidence matrix for this looks like this. And we're going to be thinking of this as an electrical circuit. I'm not going to be too precise here, but think of current flowing around the circuit, and if you want, you should think of there being a resistor of a fixed size on each edge. And so going across each resistor there's a certain current, and there's a certain voltage difference across each resistor, or you can think of that as being a voltage at each of the nodes. And the basic law from electrical circuits, Ohm's law, says that V is equal to IR. The voltage drop across a resistor is the current times the resistance. And we're taking all the resistances to be 1. I labeled the I as 1. I meant to say R. Which is to say that I is the drop in voltage. I is V1 minus V2. So this matrix is telling us something. Consider this equation. You multiply this matrix on times this vector v1, v2, v3, you get these differences. And from what I just said, these differences are these currents that I was talking about. So we can think of the incidence matrix in the following way. If you let A be the incidence matrix, and remember it has edges 1 through E and nodes 1 through N. And if you apply that to a list of voltages, what you get is the corresponding list of E currents flowing through the E different edges. And that's Ohm's law. That's just an expression of Ohm's law. AV is equal to I is capturing Ohm's law for this circuit. Okay, so let's go back and look at our example of a loop. So here's the incidence matrix, and this is what we saw. And notice that the sum of these three guys over here is equal to 0. That is to say, the sum of the currents is equal to 0. And that's a famous law from electricity, Kirchhoff's first law, which says that if you have a circuit with a loop in it, the sum of the currents around a loop has to be 0. And that's sort of obvious if you just think about the way electricity flows. There's no gain or loss of current as you go around a circuit. So let's go back and look at this equation. AV is equal to I. And remember, V is an n vector and I is an e vector. And suppose we're given a bunch of currents. Can you solve this? Does it make sense? Are there voltages which have this make sense? So for example, suppose you set all of the currents equal to 0. Well, obviously there's the 0 solution, but is there a non-trivial solution? Well, it's clear that there is. So we're asking for the null space of this vector, the null space of the incidence matrix. And let's just draw a picture. If the graph is connected, well, suppose you told me that you had some voltage on a particular node, say V1. Well, there's no current flowing, so every other node has to have the same voltage. And so that says that there is a non-trivial solution here, and it's a one-dimensional space. And it's spanned, it's all of the vectors where all of the coordinates are the same. That is to say, the null space of this matrix is one-dimensional. And that's if the graph is connected. If it had two different connected pieces, it would be two-dimensional. If it has k components, the dimension of the null space is k. That's kind of interesting right there, the fact that the number of components is noticed by the dimension of the null space of this matrix. In any event, let's go back to look at this equation that we're trying to solve. AV is equal to I. And again, we have an n vector and an e vector. Let's consider an example like this. Well, let's see. So A is a 7 by 5 matrix. So it's a map from R5 to R7. I'm not going to write down A right at the moment, but let's just think a little bit about these dimensions. The dimension of the null space of A is 1. That's what I said. So what does that say about the rank of A? Well, remember that the rank plus the dimension of the null space has to be equal to 5. So I've just computed the rank of this matrix is 4. And that's a useful piece of information because that says that the dimension of the image is 4. That's what the rank is. And notice that we're inside a 7-dimensional space, so it must be that the image is cut out by 3 conditions. Every time you have a linear condition, it cuts the dimension down by 1. And, well, every time you have a loop, you have a condition. The sum of those guys has to be 0. And this circuit has 3 loops. And so you see that the 3 loops, which are, I'm going to call them linearly independent, correspond to the fact that you have a 4-dimensional image. And what I mean by linearly independent is there's another loop here which I've indicated in green, but that's not really something new, because you can think of that as being just the sum of these two blue loops, which I've labeled 1 and 2. So I'm being slightly vague here, but I think you get the idea what it means to have distinct loops. So here I've written out the actual incidence matrix of this circuit, this graph. And now I want to look at the columns. So look at the column corresponding to node 1. So notice that it has 4 non-zero entries in it, a single 1 and 3 minus 1s. And if you look at that node, you notice it has 4 edges coming out of it. 1 is pointing out and 3 are pointing in. And that's exactly what this column is telling you. And if you think about it, the amount of current flowing into the first node has to be the amount of current flowing out. And this is Kirchhoff's second law. And let's think of that in terms of these matrices in linear algebra. Well, let's look at A transpose. I've written it out here. And now the first column has become the first row. And if we multiply this by the column vector of currents, well, the first entry I'm going to get is I1 minus I4 minus I5 minus I6, which is the current going in and out of node number 1, and that's supposed to be equal to 0. So if I take A transpose and multiply it by the column vector of currents, I'm supposed to be getting 0. So that is to say the currents are in the null space of the transpose. So in other words, I've just captured Kirchhoff's second law as the matrix equation A transpose times the vector of currents is equal to 0. So that's kind of cool that you can encapsulate this law in such an elementary statement. So let's look at some dimensions again. So what about the dimension of the null space of the transpose? Well, remember that the dimension of the null space plus the rank has to be the number of rows, which is E. And remember that the rank of A and the rank of A transpose are both n minus 1. I'm assuming that it's connected here. So I've just concluded that the dimension of the null space of A transpose is E minus n plus 1. So that's kind of interesting. We didn't have to do any calculation here. It's just you just need to know how big the matrix is, E minus n plus 1. And the idea is that the null space gets bigger every time you have loops. So for example, if you just have a circuit like this where E is equal to n, the null space is just one-dimensional. But if you have a circuit with more loops, something like this, then E minus n plus 1 is, in this case, 5 minus 4 plus 1 is 2. So here's a different way to say this, not really having something to do with circuits so much as the notion of a tree. So a tree is a connected graph that doesn't have any loops. So here's an example of a tree. And if you take any connected graph, so here's an example. Here's a graph with 4 nodes and 5 edges. Well, what I was saying earlier is that every time you have a loop, that gives you a linear relation among the rows of the incidence matrix. And so each loop cuts the rank down by 1. So let's think about doing Gaussian elimination to reduce to row echelon form. Well, each loop, as I said, it's reducing the rank by 1, and when you get down to row echelon form, well, there are no more loops. And what that corresponds to is you have a tree, and it's a connected tree, and it still touches every node of the graph, so this is what's called a spanning tree. And what we conclude is that the rank of the incidence matrix is E minus the number of loops, the number of edges, and then you lose one for every loop. Okay, so let's sort of put this all together. Suppose you have a connected graph with n nodes and e edges, and you construct its incidence matrix. So this is a map from Rn to Re. And let's think what we know about it. Well, since the graph is connected, I've already told you that the dimension of the null space is 1. And remember, the dimension of the null space plus the dimension of the image of the transpose, those two add up to n, and we know the null space is 1, and this other number is the rank, so I've just concluded that the dimension of the image of A and the dimension of the image of A transpose, which are both the same, those are both equal to the rank, and that is n minus 1. And also from our discussion, the business about the loops reducing the rank is that I know that the rank is E minus the number of loops. So what I conclude is that the rank is E minus the number of loops, but it's also n minus 1. So you get the following rather interesting equation. The number of nodes minus the number of edges plus the number of loops is equal to 1. And this is a very famous formula from mathematics. It's called Euler's formula. And it tells you about the number of, well, exactly this relation here between nodes, edges, and loops when you have a graph. And I should say, sort of, I'm sweeping under the rug the point that all of our graphs are what are called planar graphs. We're drawing them in the plane. So let's just look at one example of this. So here is a graph with 1, 2, 3, 4, 5, 6 nodes. And 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. And how many loops does it have? Looks like 4. And n minus e plus L is equal to 9 minus 6. Excuse me, 6 minus 9 plus 4, which is equal to 1. Okay, that's all for today.